Welcome back to the MOOC lectures on strategy and introduction to game theory. In this module, I am going to talk about Braess paradox. So, we have a simple transportation network. What we have is a total of 4000 motorists. Let us say they work at a place called A, okay, and they would like to go to place called B where they reside, and that is what I am saying, everybody wants to drive from A to B. Now, let us say this is the way to go from A to B, this is the path, and let us say we have a bridge here and there is another way to go like this, and in this case it is a bridge here. What we have, that bridges are sensitive to congestion, while roads are insensitive to congestion. So, we can say this part is made of bridge which is sensitive to congestion, and so is this part, and we can give this a name C and D. Now, the question is which path a motorist would take. Will he go from A to B via C, or will he go to B via D? Let us try to model it as a game. What do we have? As we have 4000 motorists, we can say we have 4000 players, we can name them 1, 2, 3 and so on. What are the strategies for player? There are two paths they can take. So, the strategy is ACB or ADB. ACB means going to B via C and ADB means going to B via D. And what is the payoff? Basically, they are interested in decreasing their time to reach B from A. So, one can say negative of time taken is payoff. Higher the number is, worse they are. Can we get the Nash equilibrium of the game? So, for that we have to give more information, as we have said that bridges are prone to congestion. So, we can say the time taken to travel from A to C, which has a bridge, depends on the number of cars on that segment. So, let us say that x is the number of car in that segment. So, if there are 1000 cars, then it takes 1000 divided by 110 minutes. Again, these numbers are made up numbers, nothing important, it is just to illustrate a point. And from C to B road, which is broad enough, so there is no congestion. So, no matter how many cars are on this part of the this road, it always takes 45 minutes from C to B. And similarly, A to D is same as C to B and D to B is same as A to C. So, here again it takes x to 100. How can we get the Nash equilibrium? This is finite game, as we have finite number of players, 4000 motorists, and all the players have only two strategies. But the problem is, again it would be difficult to draw table, as we have 4000 players. In 2 players case we can easily draw the table. So, what we can do? How can we model? We can think that we can propose a particular strategy profile as Nash equilibrium and see whether one of the players would be interested in changing his or her path. If there is one player who would be interested in changing, then the strategy profile would not be the Nash equilibrium. So, if we let us start with this symmetry argument, let us say the 2000 players or 2000 motorists would take this path and 2000 motorists would take this path. Okay? So, we have a strategy profile in which, without any loss of generality, we say that from motorist number 1 to 2000 is going to take path ACB, and from 2001 to 4000 is going to take ADB. Now, let us calculate the time taken by a motorist. Since there are 2000 motorists on this path, so 2000 divided by 100. So, it takes 20 minutes from A to C and again 45 minutes from C to B. So, everyone on ACB path takes 65 minutes. How about motorists traveling on ADB? Again there are 2000 motorists on AD. So, again 2000 motorists are on DB. So, everyone would take 20 minutes from D to B, and A to D it is given 45 minutes. So, again everyone would take 65 minutes. Now, to say it is a Nash equilibrium, we have to check whether one of the motorists have incentive to deviate or not. Let us say one motorist changes his path from ACB to ADB. What happens then? Now, he would take 45 minutes from A to D, and now we have 2001 motors on DB, not just 2000. It means DB would take now 20.01, as it is equal to 2001 divided by 100. So, total time would increase from 65 minutes to 65.01 minute. So, the payoff would decrease as the payoff is negative of time taken. So, none of the motorists have incentive, none of the motorists who are taking ACB have incentive to change their paths to ADB, and same is true for the other motorists also who are taking ADB. So, this is a Nash equilibrium. In fact, this strategy profile is not the only Nash equilibrium. In all the strategy profile in which 2000 motorists are taking ACB and remaining 2000s are taking ADB would be a Nash equilibrium. So, outcome would remain the same, that 2000 motorists would take ACB and 2000 motorists would take ADB. Now, one can say the regional planner may think that okay, this segment C to D is very near, what if we build a road? Will it help the traffic? Because it's a a building new road would never, the notion is the building new road would never make the traffic worse off. So, let us see what happens. Let us say C and D they are very near to each other. So, road takes negligible or 0 amount of time, and here I show schematically, here we have C to D, and just to control traffic it is announced that C to D people can travel only C to D, not from D to C. It does not matter if you change the direction, it would remain the same. Now, we have a slightly different game, and what is this game? Again we have the same players. So, players do not change, we have 4000 players. Strategy for each player, now we have a different strategy set. In the earlier case they could either take path ACB or they could take ADB, but now they have one more option, that is ACDB. So, there will be 3 strategies, ACB, ADB or ACDB. Payoff would remain the same, it is negative of the time taken. What would be the Nash equilibrium of this game? Can you think of what would be the Nash equilibrium of the game? Now, again we have to propose a solution, and we would check whether that is an equilibrium or not. Let us propose that all the motorists take ACDB and none of them take ACB or ADB. What happens now? Time taken would be here 4000 divided by 100, and again here 4000 divided by 100. So, they all will take 80 minutes. Okay. Now, we have to check whether one of them have any incentive to deviate or not. Notice basically C and D are the same point, because time taken to travel from C to D is 0. So, once someone reaches C, if he takes C to B, he spends 45 minutes, and even if everyone is driving on this road, time taken is only 40 minutes. So, after reaching C, it is not a good idea for any of the motorists to take CB, they will all come to this. So, they would not, none of them would deviate to ACB. But how about ADB? Again, in the beginning they have two options, either take A to C or A to D. and C and D they are at negligible, sorry, not from D to C is not possible, it is not possible to go. So, they will take 45 minutes, and again even if all of them are taking this path, then 4000 divided by 100, 40 minutes, so 85 minutes. So, we see none of the players have any incentive to deviate, and all of them would drive on ACTB, and all of them would take 80 minutes to reach from A to B. You may be thinking that what about any other Nash equilibrium? My friend, in this game there is no other Nash equilibrium. This is the only possibility. So, all of them would take now 80 minutes to reach, while in the earlier case when C and D were not connected, they were taking 65 minutes. So, building this road makes everyone worse off, and that is why we call it Braess paradox. Braess was the first one to come up with it. Braess paradox is not exactly a paradox, it is a counterintuitive result in which, like prisoner's dilemma, collective good gets sacrificed because of selfish interest. And this happens in reality also. I have given listed some example. Stuttgart, Germany, in 1969 the traffic worsened until a newly built road was closed. Same happened in New York City in 1990 on Earth Day. To celebrate the Earth Day, the 42th street was closed, and what was found? That traffic flow improves. By the way, in 2009 in New York City government decided to close down 42 street because of Braess paradox. And also in Seoul, Korea, a 6-lane road was torn down to improve traffic flow. By the way, you may be thinking that building road is a bad idea, as this example shows. This is not true. Building roads is not always a bad idea. Most of the time it improves the traffic flow, but some of the time if roads are not built after putting lot of thought or design, then it may worsen the situation. And this is observed not only in transportation sector, but also it is observed in electricity network as well as internet traffic. Thank you very much. This was Braess's paradox. We will meet again and talk about some more examples. Thank you.